Okay, let's start. So I was talking to people during the office hours, and I understood that multiple people just have problem with the homework, and specifically, the reason is that you guys just simply don't know how to debug this thing, and it makes sense to just show you. And trying to figure out the lights. Some okay, maybe this is. I just wanted to make sure that you guys are can see it. So what I wanted to show is the following. I'll just take one of the submissions. So I asked one of the students to send me their solution, and it doesn't work, right? And this is what I did during the office hours. So people come to me and I said, okay, like let's just debug it together. So the question is how, because the real goal in this class is not to just like tell you, okay, this is the operating system, it runs, forget about it. The point is to teach you the tools as well, because everything what I teach is relatively simple. Like in general, like most branches of computer science is relatively simple, as long as you understand the tooling and basic principles, right? So it's not mathematics. You know, you're not gonna be like asked to think abstractly too much. You just have to understand hardware, operating system, compilers, stuff like that, right? So we're doing operating systems, and we need to understand the tooling, essentially, how to deal with. I mean, how do you normally debug programs? You rely on your debugger. I mean, like, okay, who can tell me what debugging techniques do you guys know to begin with?
Lots of print statements.
Lots of print statements. That's perfect for a system designer like me who does operating systems, because the debuggers do not connect always. But that's not bad. I'll tell you an anecdote. We've been on a, you know, it sometimes gets very, very hard. So, you know, we were building a hypervisor which sticks itself under the Linux kernel, kind of like a rootkit, deprivileging the Linux kernel, pushing it into a virtualization container. I will explain how virtualization works later. We were relying on a printf statements. Unfortunately, we were generating so many printf statements that the buggy BIOS, which implements those printf statements and sends us those printf statements over the serial line, was crashing. Okay, so no help, just a couple of tens of megabytes of printf statements. It doesn't work. So we had to build our own tracing infrastructure. So it's a step up from printfs, where you say, okay, I will trace in a memory buffer, and when I encounter the crash, so tracing is very lightweight, so you don't print anything on a console. But then you say, look, I have some record of what was happening, right? So it's real life. There are tracing libraries for user level code. We had to build our own because the environment was so weird that we had to do it. Okay, there was another suggestion.
Breakpoints and checking.
Breakpoints are great as well. So for that you need a debugger. Okay. Later in the class, actually, we'll explain how GDB works. So what does it mean to install a breakpoint? And what else? Do you know more?
Stare at it.
What?
Just stare at it.
Staring at it. It helps sometimes. I'll give you a technique. So sometimes staring does not help, but if you try to explain the problem to someone else, you think about it differently. So try to explain it to someone. So peer debugging. So I've been on a project when I was spending weeks with my students on a single desk. Just do like a pair, what is it called? I forget. There was a term for this, like when two people program together. Maybe, yeah. So sometimes it's needed. We were not able to get through, right? So none of us. And more techniques. Imagine you have a web browser, it gets a web page and it crashes. You want to generate a bug report or even reason about the bug. What are you going to do?
See the code for the input, it crashes.
Take a look at the code for the input which crashes or what?
Yeah, like stepping step by step with the entire program. It crashes.
What I'm trying to get to is something what is called delta debugging. So it's a technique which I mean, it's a whole area of science to reduce the crushing case, because the web page is giant. What specifically crushes you? What is the minimal case which crushes you is hard. So what you start doing, roughly speaking, cut the page in half and try 2 parts. If none of them crush, you have to pick something else. If one of them crush, go with that half which crushes. And again, split it in half. So you're looking for the delta, essentially. Maybe sometimes in a real code, you say, look, you say, I'm crushing. I will add another field to this data structure. Maybe the race condition disappears, or my seg fold disappears, or something like that. Or maybe you say, okay, what was the last piece of code which I added? So maybe that is your delta. So delta debugging is yet another technique, right? So anyway, but today we will try with GDB, because I realized that people on this homework simply cannot use GDB. They just stare. Stare is not always the best way. Sometimes you ask, but sometimes it doesn't work. Okay, so let's do this. I will recreate quickly. I plan to record a video offline, but obviously I failed. And the second thing is that I also wanted to do it live. This way, it's a little bit more interactive. So homework 3 self, elf. So let me just copy the submission. And it's probably fine if you see parts of it, but it's okay. Main.c. Oops, sorry, maybe there was a different main.c here. So I assume if I type make, it will just compile. If I run it, what did we get? We get main. I will type main with an argument elf. Man, it ran. Can it be? I honestly wanted a submission which doesn't work. Real quick, that one should work. It runs but doesn't do anything, right? Question. How to debug what? Let's do fork, but not today. I need to refresh my memory. So there is this follow threads thing, and we will go through it. Yeah.
On homework 2, in the homework 2 description, it says the exact line pushing.
Right, but we can talk about it. But okay. Apparently, let's take a look at this submission. Apparently, it runs. So I expected to see a seg fold, but it somehow doesn't do anything, right? So we have familiar lines. So the person who did it so essentially says, okay, I'm gonna mmap here. That person changes those arguments to a file and header, right? Does a seek, stuff like that. Okay, so what's my next step? I don't understand what's going on, right? I can printf here, like you say, why not, right? As you said, just at least see that my infrastructure works. Printf, I don't know, like entry, and let's say p, and makes sense to just to do a debug statement like this. I put it in a background. Control-Z puts my like Vim program in the background, so I will come back to it. So I'll just run it here. Warning, warning, warning. Main elf, entry null for whatever reason, right? Yeah, go ahead.
One of those warnings tells us when the bugs.
Again,
I think one of those warnings tells us when the bugs.
Yeah, that's another thing. Okay, let's take a look at warnings. Comparison between pointer and integer. Yeah, it makes sense fixing, right? So, but that's definitely not a bug. You say file and you say, look, probably this should be 0. Null is 0 in C. So if you very well know this, maybe it's not defined. I don't really know how the standard defines it, but okay, we can fix this one. Let's take a look at this one. Passing an argument 1 of mmap makes pointer from integer without a cast. Oh, this one. What do you think is a bug here? This is an address, right? So we say, let's take a look at how I wanted this homework to look. And mmap. Well, Not sure. Why would that person pass it there? Not sure. So we can put a null here, right? For whatever reason, right? Do you agree? Another warning, passing an argument to Lseek integer from a pointer without a cast. Those, like, agree. I actually took it for, like, I was rushing and I was thinking, okay, I'll brute force it very, very fast. But I agree with you that looking at warnings is useful. C is not the most rigorous language. It's old. The warnings sometimes allow you to get through, but sometimes they're still useful, right? So sometimes warnings you can ignore, but sometimes they do fix the bugs. Do fix the bugs. Compilers like Rust are way better, right? So let's do it again. Let's take a look at what this was about. Lseek. So we clearly want to seek. Okay, I imagine for a second, I don't know the arguments to seek. So what do we do about it? Man Lseek. And I mean, maybe man is super geeky for you and you say like, what the hell? You say, okay, Lseek, and you can say, just type it like this and you will find a web page, which is essentially the same thing, but maybe pretty printed online. And let's just open it. Really? It doesn't open for me? Okay. And it tells you like this. So how do we read it? So it tells you Lseek takes 3 arguments, an integer, which is a file descriptor, and of t. What is this of t like? Unless you really understand the types and this standard library or infrastructure, you're kind of confused. So you don't know what this offset is. And int is this flag, so it kind of looks a little bit goofy to begin with. So if I, again, don't know what I'm doing, I do this, Lseek example, right? Why not? Like, many things you can read by example. Again, for example, if you're trying to learn the Rust language, which is a little bit unusual, there is a book which teaches you the Rust language. And there is another book which says Rust by example. It just says, okay, if you're so smart and you know Go and other modern languages, you don't have to go through the book. We'll just show you examples and you will understand how it works. I kind of claim that you can learn most languages besides Rust this way. Rust is very unusual, was just restricted to ownership. But okay, sure, we say, let's take a look at the example for Lseek, right? So let's open this one, optimistically hoping that it will yield something useful. Too many. Okay, we found an example here. So it says seek current specifies that the offset provided is relative to the current position. And n. What is this n? You go here and you see n is an integer. I mean, maybe not the best example, but you kind of get the handle of the fact that Lseek takes an integer as a second argument. But okay, maybe we say Stack Overflow, because these examples were designed to be commercial and just attract your attention. And this is like better. So you say, look, immediately tells you that you can use these flags as a third argument, and the offset is set to the offset bytes. Again, it's not super transparent, but you kind of understand that this is exact position in a file. And this is an example. You say in if you want to stick to the 25, this is what you do. So this is a reasonable example. Again, this is, I mean, it's not the best way to learn, but it's an okay way to learn. So do you agree that this example tells us how to use Seek? Or like, are there any questions about it? Yes, no? I mean, I use Stack Overflow a lot. My students, like, who are way better than me, use Stack Overflow a lot. Like, some people who are experts in the field post on Stack Overflow to make sure that everyone understands what's going on. So sometimes the answers are really in-depth. And if we go back to this main page, it's essentially the same. It says, okay, there are 3 flags which specify how you want to seek, and offset it should. Sometimes it even includes an example, but not this time. But okay, let's go back to this, and you will say, okay, so where do we want to seek here? So we say we know that we have some number of entries in the L file from this field phnum, right? We can actually, like, again, since we don't know what's going on, we say, okay, look, let's just print out this as well. Entries. And we'll do something like, let's say D here, just to check how many entries we found. Maybe we found something absurd to begin with. So then we take a look at this line. We say file, we're reading into the program header. Something is wrong here immediately, right? But just by staring. So who can tell me? Someone who haven't completed the homework, but still guessing. So what is missing here?
I don't know if this is what you're looking for, but the Lseek at the bottom also is the second parameter should be the offset in like bytes.
Correct. And what I'm looking in here, that we're reading from the L file, but we didn't seek. So I would assume that we need to maybe move this seek here, right? So because before reading, we want to position in a file where we want to seek, right? So seek set is correct, file is correct. So what shall be, what should be this one?
The else size, so we like read after the else header, sorry.
Yeah, plus what? I multiply maybe by size of struct proc header, something like that, right? Do you agree with this? I'm not sure I'm right. So the person says, I don't know, like the comment is confusing. It says read magic, but really for whatever reason, that person seeks here once, right? But we should probably seek more. Seek, like, man, seek like this, right? Agree?
Because we need to seek for each program header.
Exactly. Seek to the current, to the ICE if you want. Like something like that, right? So, okay.
I think we might want to use instead of the size of program header, there's a field in the L header of the size that we can might want to use that.
Size of which entry in a program header?
Yeah.
Ah, man, you're ahead of me. Maybe you're right, but let's leave it like that. I don't know whether you're right, so most likely. But anyway, so then we can read the program header. And if the type is 1, ideally we shouldn't use 1, but we should use a real like type definition, which is something like exec, right? So just a cleaner way to write the same, but it will helps readability of the code, right? Because if there is something defined, let's use it. If not, let's define it, right? So let's put it here. Then we mmap into src and so on, right? So let's see if we fix the just one variable, set but not used, variable src set but not used. Yeah, that's yet another interesting warning, which helps you to understand that something is wrong. You say, I have my source variable, I really set it to something, but I never use it, right? That's suspicious, but let's forget about it for a second. Let's just try to debug, because my goal in the end is to show you how the tools work, right? So let's try it again. Let's try running this thing and see what's happened. Entries are 2. That's believable. So, okay, first of all, how do you confirm that the number 2 for entries is a good number? Say again?
Like says the number.
Yeah, so what's the command? Readelf, yeah. .h means something like this, right? And it shows you the, like, this is exactly like this long HTML page for the homework was telling you that please use those tools to understand what's going on. And it really says that the number of program headers is 2, right? So this is good. This is a good sign. Second, it says start of the program headers is 52. We can verify it later, right? And we also say what do we see there? Let's just run it again. That the entry is null. Okay, that's not helpful, but let's take a look again. So why is entry null, right? Because we never really assign the entry, right? So we do something, but we never assign the entry, right? So we say, okay, let's assign the entry, because we know that the entry is there. So what shall we assign it to? What? Well, like, let's take a look at how entry is defined. This one, the void pointer. So kind of fine. Yeah, we don't have to typecast, to be honest. But what do we have to assign the entry to? What's the logic here? I mean, as I was saying on Piazza, it kind of works, but new one. Let me just do the drawing. So this is what we were doing, right? So we say, man, really? Oh no, this works. We created a region with mmap in memory, right? This is what mmap returns, right? Right now, SRC points here, right? Agree? What's inside that region? The way we did it here, we can say that maybe there is those last 2 arguments, which I did not recommend using, but let's quickly, let's quickly try using them. Let's do again man mmap, and it says the last 2 is a file descriptor and an offset. Okay, let's take a look at what this file descriptor is about. There's a lot about it, and we don't really know. So the intuition that maybe what we will get here is the content of that file, which we're passing here, with a specific offset in that file, right? I don't know whether it works, but at least that's the intuition, right? So, and if it supposedly works, and you had it your ELF file on disk, this is your ELF, and you have a header here, maybe some program headers here, and you loaded this section, which was executable because you said, okay, you say ph offset. This is a little weird because what you're saying here is literally no, it's actually correct. So you say, look, I read the ph, right? And ph will have an offset for the section, right? So if I read the ph, this ph, in my data structure in memory, right? And it has a fill offset, right, off. And this offset is the offset from the beginning of the file to the beginning of the section, right? Right, so that you assume that this text section, which you have here, will be mapped here at SRC, right? That's your intuition, at least. Agree? So where's the entry point? What's the address for the entry point then? Say again? In a header, you have the entry point, right? Which is, we want to guess that it points into this text section, right? So then what's the formula for the entry point here?
The header's offset plus the ph offset?
Is it the header's offset? Okay, so let me change the color here. So what you really want to compute, you say if the entry point was here, you want to compute this distance. Let's call it delta, right? Right? Or not? Because entry points into this section. Okay, hold on. This section when you look at them with readelf, what's the argument for show me all minus a? And we will pipe it to more so we don't have to go up and down. Remember when I was showing you the very first like examples of the ELF files, right? We see that each section, for example, all right, this is section headers. So we can go to the program headers here, right? It will have a virtual address at which it has to be loaded, right? Agree? So it's not a coincidence here. So if I go to the homework and if I look at the make file, what happens here is I actually explicitly specify the virtual address at which the program has to be linked to run, right? So again, I said, I mean, there is nothing special about it. I just pick the address for you to make it a little bit easier, right? But what I'm saying is that I ask the linker, this is LD is a linker, to produce a program which is linked to run at address 0, right? So it can be a different address, but the way you go about it is that you say, look, you take a look at this one, and you say, okay, look, I know that this section has to be loaded at 0, right? And the entry shows me the virtual address. So whatever this address is, right? So and it's an address, some virtual address vert. Entry is inside, right? So if you want to compute this delta from the beginning of this section into the text section, right? So you say virtual minus entry will give you delta, and since you loaded this section at some error here, in order to find the entry here, it should be the same delta, right? So then in your address space, entry is this error, or in your case, it's this SRC plus delta. Do you agree with this? We're just lucky, and we say, by the way, we're lucky, and we say that the entry point here is address 0. Wow, it's just a coincidence. It might not be 0 in general case. And the address at which we got this section linked is also 0. So the math works that it's just there. It's the SRC, right? But in a more general case, you would like to type this formula. So let's type it in. So we do this and say entry equals SRC plus delta. What's the delta? We say ph, what is this field which defines a virtual address? The error, ph, the error minus, well, let's say like this, elf entry minus phv error. Does it look correct to you? And since we say, okay, look, we kind of understand what's going on at this point, let's just put this printf again. So and say, okay, we say elf entry is pointer like an X number here, and elf on in phv error is this, and you say, let's just trace them that we read them correctly, elf entry and phv error, right? So this should help. This is the technique of adding more printfs, right? So I'm just essentially adding more printfs here. I do make again, and I run it again, and wow, it's not bad. So we say we see zeros. That corresponds to what we wanted to see, right? And if we do FG, we still think, okay, what's going on here? Why is entry this wonderful address? Who can guess?
Is it because mmap didn't work?
I also think that's probably because mmap didn't work. So that's your logic here. So you say, okay, I see this weird address, so clearly something is wrong. So I will again do a printf and see src here and check whether mmap really worked or not, right? Let's run it again. We do, oops, sorry, so make, and this complains because it's an address. So let's, again, since we're pure now, we say, okay, let's fix all the warnings. We, instead of actual, put p here to say that's pointer. Control Z, make again, runs. src is this weird address. You kind of have an idea that this address is a little weird, looks a little magical, right? All Fs, right? So good hint that mmap did not work, right? So again, look, let's take a look at this mmap now. So what does the assignment tells us to do, right? So it says first argument is null, phmem size. Okay, we need the size. So we have the size here. We can trace it just because we don't trust ourselves. We say, okay, oh, I wanted to say printf again. Mem size, again, div or x, I don't know. Huh? Whatever you like more. D is like decimal. Mem size. Let's do it again. We do, oops, Control Z, we make again. Let's run it again. 48. How do we check it? We go again to readelf. And let's go to this program. Mem size 48. Kind of matches, right? So that's a good sign too. We read it. So it's a hex number which we got from our code, right? And this is what we've seen on the screen. So let's confirm it again. It says 48, right? So that's a hex number, right? So this is correct. So let's go back here. We say, what is this mmap doing in general? So why do we use it?
Mmap gives us a point in memory that's going to be the size of the second argument.
Mm-hmm.
And then the difference between the one you posted and the one in the that we're coding right now is the last two characters are 00 on yours.
Yeah.
Presumably we wanted to like set it later, not just on the go.
Probably, right, but just again, for everyone, clarify, why do I even use this mmap versus just malloc, for example?
It allows you to set the permissions additionally to malloc. You can will reserve page for you. With mmap, you can also say, oh, I want this page to be executable as well, which malloc probably doesn't do.
Correct. So how many people know that memory which is allocated by malloc cannot be executed on modern machines? It's again, I don't think it was always this way, but since like in the last 20 years, we've seen a huge spike in the security attacks where like people from overseas just break into your bank account or whatever, your Bitcoin's account, and just steal everything. People started like making software is a little bit more resilient to those targeted security attacks, because it's a big business, you know, like for people in Ukraine, I'm from Ukraine, right? So like, you know, I had friends who were doing various interesting things, like removing DRM from, for example, from games, right? So it's a lot of money, right? So breaking into machines overseas, it's hard to prosecute, right? So it's a profitable business, well-funded. So at some point, people said, okay, malloc will return non-executable memory, right? So it's just a security mechanism, right? So in order to make sure that we can allocate memory which we can execute, we have to set this flag, along with these two other flags, like readable, writable, anonymous, and private. I forgot what this exactly mean, but they probably just say, it says that mmap is not trying to mmap a specific file, but just give us memory, essentially. That's what it says. Okay, so but clearly it's failing. So we can either go ahead and read this this man, Or we can try to put zeros here, right? And see whether it helps, right? So we will do this, and make again, run again. SRC returns an address which is at least looks like a regular address, right? So that's better, right? But we're still crossing, right? So at this point, what's the next step? Let's, again, as you say, first stare, right?
I'd probably try to figure out where we're using a call address, something like that.
Say again?
I'd probably try to figure out where we're using undefined memory or jumping to format addresses, or, for example, casting an entry pointer, which is a 0 to a function.
Actually, you lost me a little bit. Let's try your version.
The mmap allocates memory, but we're not actually putting anything inside of that memory.
Correct. So essentially, we just allocated memory, but there is no text section from the L file there, right? But let me show you a trick here, because in some submissions, the memory was there, but it was still crushed. And let me show you how you go about it. So you say, I don't really know. So I don't really know, but it's clearly crashing. So segfault. So let's invoke our wonderful machinery of GDB. So how do we use GDB in this setting? I mean, maybe in all your classes, the debugger was coming integrated in a whatever software development environment which you are using. Maybe it's Visual Studio. I think today Visual Studio is so good that it integrates GDB seamlessly as well. I didn't use it much, so I don't really know. I use a GDB as a standalone debugger just because it's integration with, when you start running x86, most likely it will break. It's easy to fix, but you need someone who understands how to fix it, integrate it with Visual Studio. That's why I say, let's just learn how to use GDB. And this was the point of the homework number 1, learn how to use GDB. So, okay, so how do we invoke GDB on this example?
If you don't need the main, just GDB elf. Need the main, I think it's GDB /args, and then you pass in main and elf.
Do we need elf, or do we need main? We clearly need main, because elf is not even running yet. So elf is yet another binary, right? So main is crashing. So this is GDB, right? So, okay, we got it. So we say we can run it. It crashes in a very similar way. I can use a backtrace similar to how we did it in the previous homework. And it says, okay, it crashed at this address. I say disas, essentially saying, maybe you can disassemble me something. So not super helpful, right? So we say, okay, that's kind of ugly, those hex addresses. I don't understand even what's going on, right? But I was trying to teach you that there is this tool, TUI, what is it, terminal user interface. And I switched to it, right? No source code available. That's yuck. And we say, cool, yeah. But do we know how to get the source code?
Break it. Break one out.
No, first of all, why is source code not available? Correct. And that was there in the homework 1 to learn how to compile stuff with debug information. Maybe I opened it twice, so let's split here in a make file just to make it. Well, I don't know. Maybe it haven't. Recover. Let's recover. I don't know why we have to recover. So who can tell me how to compile? What kind of flag we need to add? It actually says G, right? So it should have debug info, right?
It's already finished executing. So.
Yeah, you're not breaking it so that it can read, so it pops up for a second and then it stops.
Okay, maybe you were right. I was wrong. So TUI enable again. Still says us no source code. So what's going on?
Do the TUI enable, go to the process menu, break main or bmain.
Bmain.
And now run.
Yeah, clearly source code is here, right? Okay, let's run. Really, yeah, we do have the source code. We are in main. I'm still trying to use my TUI. And magically showed up. Don't know what the glitch is, but now we are inside main, and we can start executing line by line, right? So I N stands for next line, right? And we say, look, let's execute a little bit, like open the file. We clearly know that we can go to entries, read this thing. This is not crashing. This wasn't crashing either. So we can go forward. We see something on the screen. It reads some entries. But I mean, it's not like your Visual Studio, but it's not super horrible. At least you have the source code. It's a separate screen. You can see what's going on, right? Again, why am I wasting time on this? I want you to understand that, okay, this is a useful tool. In the future homeworks, when you're going to be debugging x86 kernel, this GDB will come handy. Essentially, some of these homeworks are hard to do without it, right? Okay, so this was fine. So let's try this, and then boom, we crash here. And by the way, source code is not available. We say backtrace, and actually in this frame, the source code is not available. But if I say frame one, frame one, right? Essentially, I believe that it just, because we jumped into some memory for which GDB doesn't have debug info, because we jumped to an address which will allocate it with mmap, right? GDB just says, okay, like there is no source code there, right? But it was there before, right? It was before we jumped to that address, right? So okay, so we crashed here. We say, okay, let's run it again from the beginning, right? This time we can scroll in this window, say, okay, let's maybe break on this line, break on line 115, right? Agree? Because this is where we crashed. We say continue. So I'm right here. I'm like my tool window went to hell. Let's to the like maybe Control L to make it sane again. I can type a list command, or I can say to disable, just to make sure that I'm on that line. Hey man, where am I? On which line am I? That's the question. To enable again. Maybe it will show me. I hope. Oh yeah. This highlighted. So kind of believable that we're on that line. So and we crash on that line, right? I mean, so what's the next step? What are you going to do at this point?
Inspect the memory at address something.
Inspect the memory at address something. Okay, which address?
Well, some.
Some. Okay, so what is this address? How do we get it? psum. So psum shows us, okay, this is actually the address, right? So P stands for print, right? And it's useful. So then how do we expect memory? X. And we say sum, for example, right? Well, not super clear because it says just all the zeros. So I will help you a little bit here, and I say, what is that? B, sum again. So which means I asked GDB to print me just 1 byte, right? But still, it's a little bit ugly, and I say, look, like print me 20 bytes around sum, right? Just to make sure that I understand that the numbers I'm staring at, those numbers are what I want to see. And I said, okay, look, I say print me 20 bytes from this address, and it says 1, 2, 3, 4, 5, 6, 7, 8, and then it increments by 8 here, and again prints zeros, right? So clearly something is going on. So clearly we're jumping to memory, which is all zeros, right? What do we expect to see in that memory?
Executable code.
The executable code. How do we find what this code should be? Maybe 0 is a valid instruction. How do we know? Looks suspicious, I agree, but
From the ELF executable file.
Exactly. So we go back to the ELF, and which command do we use?
HXX. Yeah, we can transfer the executable file to the text file.
Right. But remember earlier in class, I was showing you a different tool, which was exactly object dump. So object dump, we say, who remembers how to call it? I don't. And you say /d, disassemble this one. I agree. Object dump minus D, and then L, right? And man, this is what we should probably expect to see: 55, 8, 9, E5, right? But we clearly just see just zeros, right? And this code actually makes sense because you say, what is sum doing? It adds two arguments. Arguments are on the stack, right? We said, okay, preserve the stack frame with the EBP. This is exactly what I was trying to explain earlier. So arguments are passed on the stack and they're relative to the EBP. And thanks God we maintain the stack frame. So the code is not relative to ASP, but to the EBP. And it's EBP plus 8 and EBP plus XC. And if you say, I hate it because I don't understand what's going on, let's just switch to an Intel format. How do we do this? Do you remember how to switch to Intel? By default, it prints out the AT&T syntax, but okay, like since I was mostly using Intel, you say obj dump Intel syntax, right? Because okay, maybe I don't remember either, so and I don't really. Again, we go to Stack Overflow and say, okay, oh, clearly this is something what we want. So minus M Intel, right? Okay, let's pass it here and do it again just to confirm our theory that, okay, we see what we want to see, ALF. So, man, minus D, right? Okay, this is exactly what we were doing in class, right? So EBP plus 8, Intel syntax, that's one argument, EBP plus C, another argument, into registers EDX and EAX, and then we add them, leaving the result in the EAX, of the stack frame and return. So clearly this is the sum function, right? That's why we spend so much time on assembly, because now we understand that, okay, this code makes sense, right? Again, spending time on this, because in the later homeworks, when you will be modifying the x86 operating system kernel, starting new processes in it, starting new threads, you will have to confirm that whatever you're starting is really what you want to start, right? So this is the way to do that. And again, maybe my examples in the lectures were like a little detached from reality, right? But this is a connection. So this homework, right? Plus the homework 1, which was asking you to essentially figure it out. Okay, at this point we say, okay, clearly something went wrong. We're trying to execute zeros, but again, just to make sure that we understand that, okay, this line is sum, but what's going on inside? So let's just say TUI layout ASM and layout ASM, and just there is a thing which allows me to do step into, right? So right now I am on this line in my assembly file, right? This is the call to sum, right? Because we were calling a function pointer, the call goes through a register, right? But if I want to confirm that I'm doing what I'm expected, the GDB does what I'm expecting, okay, whatever. It does what I want, right? So we say step instruction and say, okay, we allocated some space on the stack Y.
Quick question, what's there between step and next?
What's the difference between step and next? Step, if there's a call instruction, step will go into the function, and next will walk over without going into. So what is this? We subtracted 8 from the ESP. What are we doing here? For what? Exactly. So what we're doing, we are making room on the stack so we can push. Actually, no, we're still pushing. So push will allocate space on its own. So what are we doing? I'm guessing we're actually preserving the alignment, because I think it GCC generates the stack which is 16-byte aligned. And so that's why we're pushing 2 arguments, which are 4 and 4, which is 8. And we allocated another 8 to make sure that the stack is 16-byte aligned. That's my guess, right? Not 100% sure, right? So, but anyway, so we're pushing 2 arguments on the stack. We're pushing 2 and 1, and we can double check that this is exactly what we want, right? So this is the make file. So we say v minus r, right? That, right? Just to, because the other one is over there. what is this sum function? So how do we invoke it? We invoke it with 1 and 2. So clearly 1 and 2 is a good sign, right? So that's fine. So we're pushing, and when I press enter now, it just like repeats the last command for me. So it's step instruction. So we push 2 arguments on the stack. What is this nonsense? Ah, okay, well, yeah, by nonsense, okay. What is this? What is this line?
You are loading the function address from the register EAX.
Correct, right. So we are, our variable sum is currently in this, on the stack relative to EBP, right? So we're loading it into the EAX register, right? And then right now we will do this call instruction through EAX. Since I'm doing step instruction, I will walk in, and that's my memory. Surprisingly, GDB tells me that this is a valid assembly instruction. It's actually addition, right? I told you that 0 might be a valid assembly instruction. It actually is, looks like. Agree? I mean, we don't have to trust GDB. We can go into the instruction tables, but this memory at this address, CE000, which is 0, right? It's exactly the same address which we're currently executing, right? So then why do we crash? Sometimes it happens, right? But what is happening here? We're gonna crash in this very next instruction in a second. Because of what?
We're reading EAX.
Yeah, we are actually writing. So this is the AT&T syntax again. Sorry, I forgot to switch. But essentially, this instruction adds the value which is inside the AL register into the memory pointed by the EAX register. And let's take a look. What is the value of info regs? Info reg. We might not crash actually, right? So EAX, I was naively expecting to see that EAX is 0, but I mean GDB, there's this command that shows you all the registers, and this is the address which we just actually allocated. So we will probably write the same address, right? Let's try it. We will not crash immediately, right? Step in. Oh man, yeah, it runs, keeps running as you were predicting, right? Which is kind of a game, this is how this, some of those bugs are confusing. So you don't crash immediately. You keep walking for a while until something really bad happens, until, I don't know, like you can go here for quite a while. I'm pretty sure that since this instruction doesn't really change the state of the program in any bad way, right? So you can run until you, as you said, until we reach the end of this M-mapped region. If it's all zeros, right? Agree with this? Most likely we will. And that's why essentially we say, if I say continue, it actually crashes at this address, right? So if we take this address and we take Python here and put this address here, and we just said, okay, what was the address which we were printing, where the sum was, this address, and try to find the difference between these two. It's quite a big region of memory, right? So who knows? Maybe something else happened. Maybe not. Maybe mmap allocated this big of a region, right? So maybe let's see if it's square to something, right? So maybe it's like a page size or something like that, right? Yeah, it kind of looks a little square. So probably mmap allocated multiple pages, put zeros there, and we ran through them. So like we didn't want to see it, right? Okay, so fun, but we kind of learned how to dive into it. So now how to fix. Let's go back to this. Let's quit here. So our current hypothesis is actually that we're running this. Remember we're running this region. Oops, sorry. Man, it took me the whole time actually. So we're running somewhere here, right? But there is nothing meaningful here. We didn't do copy or load from a file, right, into this region. Agree? That's most likely this is why we're failing, right? Okay, so how we do this? At this point, we stare. Okay, who can tell me what to type? I'll start. Read. What's our file? It's file. Where do we want to read? Inside the SRC, right? How much do we want to read? ph, mem size, right? Agree? But we need Lseek first, right? So, and I agree with that. Lseek file alpha where? ph off, because this is the offset, right? So this is the ph off right here, right? It points to where this thing is in the file, right? And we do seek, what's this? Set, right? So this seems reasonable, right? We do make again. We try to run it. Can do with GDB. Man, miracle, sum is 3. But again, at this point, we can just quickly submit if it's like 10 minutes before the midnight, right? But if we still have a little bit of time, let's just confirm that we got what we wanted. So GDB again, TUI enable, breakpoint on, or like we say run. Then it gets us, I think it's ran, so we say breakpoint on which line, on where we were doing sum, breakpoint on 118. Control L, run it again. So we're here again, and at this point, as you say, let's inspect the memory. I say TUI disable so I can lift commands from history. So, but no, I'm not lucky. So again, we say x slash, let's say 20 bytes from the address of sum. And how do I do this? It printed me bytes, right? But what if I want to do hex? This is better, right? So why is it better? Because this 55 is my lovely instruction, which I'm looking for, right? So remember, I said where is it? Obj dump again. Okay, we don't have it. Obj dump. Obj dump minus m intel minus disassemble elf. So this is what I wanted to see. I wanted to see 55, 89, E5, right? And so if I go here, I see them. I see 55, E9, 89, E5, and stuff. I can do this disaster of sum. Oops, sorry. And hopefully it will not fail at this point. How do we do this? Like this? Can I do something like disassembly of this address? Hopefully it should work, right? Fails. Maybe there is a way to force it, but I don't know, right? So what I'm trying to claim that you can actually force GDB to disassemble those addresses, but okay, whatever. So again, TUI layout, TUI enable again, just to see that we're gonna do it. Layout as in that we're executing something meaningful. Step instruction again, same kind of thing. Jump to this function, and hooray, we're executing what you wanted to execute. So this is part of the elf, which implements the sum, right? So this is where we return. We return from this call. I say layout SRC again to make sure that we switch to this one, and I say next and print, and I'm done, right? So I'm happy. So this is how you should approach this. So the point was to help you with this tooling. So essentially using GDB on those kind of counterintuitive cases, and using obj dump and readelf to understand how it should work as well, right? Okay, let me stop for a second. So questions, we have 4 minutes. Yeah.
On like the little whiteboard thing that pulled up, you calculated the offset to read into the file with the for the delta being the virtual minus the entry. I'm just a little confused why it ended up in the code. It ended up doing entry minus.
Yeah, I was wrong here, so man, sorry, I apologize. So it really should, because entry is clearly larger. So if this is the entry, so I was wrong. So it has to be entry minus virtual. Thank you.
Wait, so is the entry at the beginning of the program header?
No, entry is guaranteed to be inside the text section, right? It gets a little bit more complicated when you have multiple text sections. And at this point, my assignment breaks because I say, look, how to even solve it if you have multiple text sections? It gets complicated. But for this specific, I wanted to show you just a simplified case, which might not be super realistic, but still, you get the point how you load the program from disk to memory, right? And the entry will be always inside this text section. It's not guaranteed to be at the beginning of the text section, but it's guaranteed to be inside one of them, right? So a more general solution probably is to load all text sections, figure out where entry belongs, right? Because it belongs into one region. So you have to do a comparison here and then figure out where you loaded that specific section, which has entry, and then jump to that, right? So it's a little bit more complicated, but I haven't done it because there is just one. And I confirmed it with ELF, read ELF, right? Any other questions?
I think class is at 10:30.
Ah, 10:30? Cool. And so I always send it to 10:20. I always, no? Oh, cool, yeah, I didn't know. You're kind of right. Sure, then we can keep going a little.
So the reason it was breaking was because we were walking too far, so to fix that, we didn't Lseek to put us in the right place, so we wouldn't walk so far.
No. No. The reason was, sorry, let me quit and let me show you again. We didn't have those lines at all. So we didn't have anything in the memory which we allocated with mmap. And mmap initialized the memory with zeros for us. And we jumped there, and it was a valid assembly instruction, which was this addition of AL into the AL pointed in by the AL register in memory, right? And we could single step it forever, like for thousands of times, right? But eventually we reached the end of this segment and crashed, most likely, right?
So it would step until the end of the
I think so, yeah. We didn't confirm it, but that's what logical to assume, right? I mean, this stuff comes up like really like I build operating systems, right? So and I was lucky to program a little bit more back in the day, so like 2 years ago. Right now I'm a little busy like typing some nonsensical stuff on my computer, right? But once in a while I still program, right? And but even without operating systems, it just comes up. Imagine you have some funky trick which you do in a C++ Boost library. Okay, good luck to you debugging Boost, but something maybe more realistic. I don't know, some Apache web server or a key value store, and you suddenly like jump to some address and something crashes in some unpredictable way. So this is the way to go. As long as you can connect your GDB to this program, and GDB is very powerful, you can figure your way out. And sometimes if you cannot do GDB, do the printfs. And the way, if I wouldn't have GDB, I would do the same with printf. And I did it in my real life, I did it. So like, if there is no GDB, which can connect to my Linux kernel, which is crashing, I will start dumping memory at this address. I would write a for loop here in front of this sum. I know that I'm crashing in sum. I would write a for loop here, which would dump memory in sum for me to understand what is that I'm about to execute. So it happened to me multiple times again. So again, it's if you don't have GDB, just do the same, but manually with printfs. Any other questions? Good. Okay. So hopefully now everyone can understand how to do this, how to finish this homework. And again, it's fine. I mean, I appreciate the fact that some people have already submitted. I mean, was debugged or like pushed through this, maybe just by pure luck or by talking to us, or by just like doing the same techniques, because some people can do them, right? So in this class as well. But I think it's very useful for everyone else to understand. So next time, if something like that shows up and you say, look, I'm stuck, and I don't know the tooling which will allow me to push through the homework, we will do it again. Like we'll do the same debugging section in class, and we're lucky we have enough time to do that. Okay, so then again, if no questions, I will stop because it probably doesn't make sense to start a new one. We'll finish address translation. I'll actually try to assign the quiz right away as a promise, and it will cover address translation, right? And then I will see you on Tuesday. It's a long weekend, so I hope you will enjoy it somehow. I would go skiing if I were you or somewhere.